Bootstrap sampling distributions are useful when formulas or the central limit theorem cannot easily determine the sampling distribution of a statistic. The central limit theorem works very well for sample means, but many statistics do not satisfy its conditions. In those situations, we need another way to understand the variability of our statistic. There are several situations where the central limit theorem may not work well. The statistic might have a complicated distribution, such as the median, a trim mean, or a percentile. The sample size might also be too small for normal approximations to be reliable. In other cases, the population distribution might be strongly skewed or heavy-tailed, or the formula for the standard error might simply be unknown. When these situations occur, classical theoretical methods become difficult to apply. Mathematical derivations can be complicated and the resulting approximations may not be accurate. In these cases, we look for an alternative approach that relies less on theoretical formulas and more on computation. Bootstrapping provides that alternative. Bootstrapping is a resampling method used to approximate the sampling distribution of a statistic. Instead of relying on theoretical formulas, we use the data that we have already collected and repeatedly resample from it. The key idea is to treat the sample as a stand-in for the population. The term bootstrapping comes from the phrase pulling yourself up by your bootstraps. In statistics, this means that the sample is used to learn about its own variability. By repeatedly resampling from the observed data, we can study how the statistic behaves across many simulated samples. The key insight behind bootstrapping is the following idea. If the sample is representative of the population, then resampling from the sample mimics the process of sampling from the population. This allows us to approximate the sampling distribution of the statistic using only the data we already have. The basic idea is simple. Instead of imagining many new samples from the population, which we cannot actually obtain, we repeatedly resample from our observed data. Each resample produces a new value of the statistic, and together these values form an approximation to the sampling distribution. Suppose we start with a sample of size n. The first step in bootstrapping is to begin with the original sample, and then draw a new sample of size n from it. Importantly, this resampling is done with replacements. This means that the same observation can appear multiple times in a bootstrap sample. After creating the bootstrap sample, we compute the statistic of interest for that sample. Then we repeat the resampling and calculation process many times, often thousands of times. Finally, we examine the distribution of all the computed statistics. The distribution formed by these repeated statistics is called the bootstrap distribution. This distribution serves as an approximation to the true sampling distribution of the statistic. By examining this distribution, we can learn how much the statistic varies from sample to sample. As an example, imagine a study measuring the diameters of 25 tumors detected in a mammogram screening. Because the data are skewed and the sample size is relatively small, we may not want to rely on theoretical formulas to describe the sampling distribution of the median tumor size. Instead, we can apply a bootstrap simulation. We repeatedly resample the tumor measurements with replacement, compute the median for each resample, and then examine the resulting distribution of bootstrap medians. The histogram on the slide illustrates this bootstrap sampling distribution. Each value in this histogram represents the median calculated from one bootstrap sample. By looking at the spread of these values, we can estimate the variability of the median. This allows us to estimate quantities such as the standard error and confidence intervals. Bootstrapping is especially useful when the sampling distribution is mathematically difficult to derive. It is also helpful when the statistic is not well handled by the central limit theorem or when the sample size is modest. In these situations, computation provides a flexible alternative to theory. From the Bootstrap distribution, we can estimate several important quantities. These include the standard error of the statistic, confidence intervals for the parameter, possible bias in the estimator, and the overall shape of the sampling distribution. However, bootstrapping should be used carefully. The method works best when the original sample is representative of the population, when observations are independent, and when the sample size is not extremely small. If the original sample contains problems, the bootstrap will reproduce those problems. A biased sample will produce biased bootstrap results, and a very small sample may not capture the true structure of the population. To summarize, there are two main approaches to statistical inference. Theory-based inference derives sampling distributions mathematically from probability models. Bootstrap inference takes a different approach. Instead of deriving formulas, it approximates the sampling distribution computationally using repeated resampling. When formulas are unavailable or unreliable, bootstrapping provides a practical and powerful way to study the variability of complex statistics.